international perspective on this is to be able to say that the results I obtain in terms of the role of technological innovations in influencing stock returns is not something that is only valid for a particular country. Right? So typically in financial economics, it is quite common to have applications based on the US. So as a result, we know a lot of things.
Is that I estimate the economic value of technology or technological innovations for investors in these 12 countries. So the story I'm going to tell you today about the role that technological innovations play in predicting the stock market returns has got statistical story as well as a economic story. So if you are an investor who would want to depend on technology, you would be able to know how much return you can make if you use these models, statistical models that I am proposing. So that's basically how I'm going to address this. Now, methodologies. I want to spend a bit of time explaining what I do in the methodology to construct the what I call the return-based technology factor. So again, I emphasize that I don't use patents granted as a predictor of returns, right? But I use that information to compute return-based technology factors, and the inspiration for doing this comes from a paper that was published in the Journal of Econometrics in 2001, where these authors, they developed a portfolio tracking approach which can capture the market's expectations about the future. So I use an augmented version of that model to develop a return-based technology factor that will reflect the market's expectations of future technological innovations. This is important because we want to know what is the expectation of the market from technological developments, not the other way around. Okay? So a straightforward way of answering the question that I put here would be to run a regression of stock returns on patent granted to residents. Okay? But that would be a negative way of capturing the effect of technology or patents. Why? Because as I explained, if a patent is granted today, the effect would be felt, no, it could be 10 years, it could be 20 years, right? But if you compute the market's expectations of the technological innovation, then you are fine. You have more, you have a rich information variable, which is technology based. So I want to show you how I construct that. Okay, so there's two ways I do. I take the patents granted to residents, so that data is there from, as I said, for many countries from 1870 to 2012, 2013. I detrend it using the Hodrick-Prescott filter, detrending filter. Then I regress the 1 year detrended shock. So I call that detrended patent as tech. T+1 means the 1 year ahead. And I regress it on axis expectation of technological innovations in the future. So this is what tells me the market's expectation, right? So C1 here. Now, impact of market's expectation on technological innovation. So how do I do that? Well, if I run this as a rolling regression, so if you're familiar with rolling regression, you know that you can run this regression X number of times, repeatedly, by setting an initial window. So what I do is I estimate that equation using 20 to 30 years of data, and I obtain parameter estimates all the way from T to T+1. And this is what I get. So here's an example for Australia, right? So Australia has got data from 1870. I use 30 years of data to run my first regression and I get a C1T for 1900. So that's the value there. Right? So this, all the way I do it to 2012 using a rolling window of 30 years of data. So what you see, this tells me the market's expectation of future technological innovations, right? Okay. Over time. Here's an example for what I get for US. So a positive value means that the market is going to react positively to technological innovations and vice versa. So here's a time varying C1. Okay. All right. So in that way, what I have done is I obtained, as I said, a time varying parameter relating to each variable in our regression model. But of course, the relevant variable here is to compute the based technology factor, which I call it RTF1, and that relates to C1. Once I get C1, I then multiply it by the excess stock market return. Right? So it's quite simple. So if we just go in here, once I have got an estimate for C1T, like in the case of Australia, I got a C1 for 1900 and a C1 for 1901, C1 for 1902, all the way to 2012. Once I have the coefficients of this, I have created a new variable which is a technology-based return factor. Now, why is it a return factor? Because I took the coefficient E1 and multiplied it by excess return, right? Such that it forms the market's expectations of future technological innovations. Okay? So this is the innovation, leads to this regression model. Then I also consider the literature which says that when you talk about historical stock markets or stock markets in history, stock prices in particular, you will find that there are structural breaks in these stock prices, right? Stock prices are well known to be characterized by structural breaks. So essentially, when you look at this model, I don't have anything to do with structural breaks. Okay? In a subsequent model, I introduce the structural break as an additional variable in the model. So that's the dummy variable for a structural break. So in between here, I do a formal test for structural breaks in the data. Okay? And I'll show you the results later. So there's an additional step involved between these two equations is a test for structural breaks, and I find what others have found, that the stock prices for these 12 OECD countries contain a structural break. So obviously what it means is one needs to model the structural breaks. So it's easy to expand or augment that regression with a dummy variable that captures the structural break. Okay? Of course, the advantage of the structural break is that if you know what the structural break is, you can use that structural break to create regimes. So you can subsample the data. So the way to think about this would be if US stock price has one structural break, and you know the break is 1958, then your first regime or first subsample could be 1870 to 1957, and the second regime would be the structural break one, 1958 to 2012. Right? So you can test actually whether the structural break actually influenced the predictability outcomes. Right? So there's two advantages. One is obviously you are directly modeling the structural break to ensure that there is no misspecification of the regression model. And the second is you can actually create regimes based on the evidence of structural breaks. So I do both in this. Here is a snapshot of what the data looks like. So 12 OECD countries, this is the main stock market index of this country to 5 per annum. Right? That's the raw returns. Excess returns, this is in excess of the risk-free rate. It's minus 3.47 to 1.2. And real returns, so here I adjust for inflation. It's about, when you adjust for inflation, the range is more broader, minus 7.5 to 0.0%. So what this tells you is that there is, even though we consider 12 OECD countries, there is quite strong heterogeneity simply from the market itself, which may mean that the implication is that the effect of technology could still be very different, despite the fact that we have a homogeneous group in the sense that we have OECD countries, right? Just to add to that, Germany, Italy, Japan, that these three countries turn out to have the most volatile markets when you look at that 100 to 140 years of data. Right? By comparison, US, UK, Canada, and Australia are amongst the least volatile markets. So, from a volatility perspective, you still have markets that are vastly different. And the implication is that technology could still have very different effects on these markets, although here we are talking about advanced economies. So I just wanted to bring that that story on returns and volatility. And when I look at the data on patents granted to residents, again, this tells a very different story for each of the OECD countries. For all of them, the common thing is that the patents granted has grown, and grown quite rapidly over the 100 odd years. Italy, though, has the highest annualized growth rate of patents granted, 44% per annum from 1870s. That's quite a strong growth in patents, right? And you compare the other countries like Japan, patent growth about 11% per annum, which sounds more sort of reasonable. Spain about 10.94, Finland about 10.85. So not only in terms of mean returns and volatility of the market, but also in terms of patents granted, you see that the countries, they are very different from each other, right? So what we see happening here is within the advanced economies, not only the stock markets have been behaving so very differently, but the magnitude of technological innovations have been vastly different. The implication being that when we actually do the formal test later, including the economic value test, should be able to find, these statistics suggest, vastly different results for these OECD countries. And that's exactly what I find. So we'll look at that. Okay, so here's the result. Before I get to this, like I said, I compute the technological innovations by taking the growth rate of patents granted and detrending it. Right? Later I do a robustness test where I also run an autoregressive model in the RTF, Norway, Spain, UK, and US. Right? When I use the IR5 measure, what I call RTF2, I find that for 11 countries there is quite strong results here, although the results would improve with the other factor as I do additional tests. But the consistency in these results is that there's one country that stands out for which there's no evidence of predictability, and that's Denmark. Right? So no matter which model you use, and also an additional test as I'll show you, Denmark turns out to be a country where there's no predictability. And the reason seems quite straightforward when I look at the data. Denmark has been one of those countries where technological innovations have been on the lower side out of the OECD countries. This sort of signals to the fact that there's some sort of threshold level of technological innovations that are needed for technology to actually have an effect on the stock market. All right. So here's the additional. Remember how I talked about the structural break and break date? So when I test for structural break, these are the dates. So I restrict it to one break. And there's a good reason to restrict it to one break, because 2 breaks would make my subsampling too small. So I don't want to lose too much of the data. So I had to compromise between choice of the number of breaks as a result. So you can imagine if I have 2 breaks, then that will lead to 3 subsamples. And there will be much better than when you have one break and 2 subsamples, right? So here are the breaks. So the breaks are again quite different. Although for US and Canada, breaks are quite close together. 19 Italy, Norway, Spain, and US. The regime does not matter. Predictability is almost always there. In other words, the long sample does not really matter for these countries because I have been able to find predictability with a small sample. Okay. When I use the R2 method, which is the of residuals, again, there's predictability of 10 and 8 countries in these 2 regimes. 7 countries out as being regimes. Canada, Finland, Germany, France, Spain, and US. And this is what comes out. So when I include the structural break dummy variable, the RTF1 for 9 countries and RTF2 predicts returns for 11 countries. So take together, out of the 12 countries, there's 1 country for which I find absolutely no evidence of predictability, and that is Denmark. All right. So from these results, I mean, these results are very much consistent with what I was telling you earlier. From these results, one of the main conclusions we can make is that yes, there is some changes in the number of countries which predictability found, but the results are robust in the sense that structural breaks only improve the evidence of predictability, if anything, right? You don't lose any of the results that I explained you earlier. If anything, it becomes better, although only slightly, but the fact remains that the results are robust to structural breaks. Than the historical average, then the out of sample R squared should be positive, right? In this way. So I'm looking for positive out of sample R as a way of arguing that the technology-based forecast would be superior to a forecast that is based on historical average. Okay, so this is the statistic I compute from my model, and I compare it with the historical average model. And one of the things to consider to do forecasting is the sample period. So what I do is I take 50% of the sample, and then I forecast returns for the remaining 50% of the sample, right? And what I find is that for 11 out of 12 countries, the out of sample R squared is greater than 0. So this should not be Japan, it should be Denmark. There's made a mistake in here. So when the out of sample R squared is greater than 0, it tells that my proposed technology model gives you less errors in forecasting than a historical average model. Like I found with the in-sample evidence of predictability, there are 11 countries for which there is strong evidence that technology-based factor predicts returns. And Denmark is the only country for which there is no out-of-sample evidence. So what we conclude is from both in-sample and out-of-sample test, the evidence of predictability is there for 11 out of 12 countries. Okay. Now, you may ask, why have I done all these different tests? Why I could have just stopped at the in-sample evidence. This is part of the robustness story. Okay? So I did an in-sample model. Then I wanted to be sure that is a country that stands out as having no relationship between technology and stock returns. And it's typical in this financial economics literature when you are doing in-sample test to out-of-sample test. And typically out-of-sample test is taken as a robustness test. Okay? So now I can be very confident that I need to exclude Denmark from any further analysis. Drops out. Right? All right. So what is the implication so far? Implication of the results so far. Before we look at the economic value of technology factor. Right? The literature on stock return predictability. So there is a huge literature on stock return predictability, right? Almost everyone wants to know what would be the stock returns tomorrow morning when we wake up. When we look at this literature, traditionally, in financial economics, what people have been using is financial ratios. So this has been, you can think of this as a traditional set of predictors, financial ratios. So what are financial ratios? These are book to market ratios, dividend yields, cash flow, price earnings ratios, right? And the focus of this literature when it comes to predicting returns has been on financial ratios. And you can easily identify, 50 odd papers in the very good journals that would have done this. And yet they do not find conclusive evidence that financial ratios are able to predict returns. They find mixed results. So these results are country specific, these results are dependent on methodology, these results are also dependent on the data sample size. There is no conclusive evidence yet to say that all these financial ratios predict returns. The most common financial ratio that predicts returns is the book to market ratio, right? But on the other ratios, there is debate. What I do is I use non-financial ratios. So the patent-based technology factor has got nothing to do with financial ratios, right? So I use a completely new predictor. And I show that for 11 out of 12 countries, there's robust evidence, right? So I showed that regardless of whether you use detrended patent growth or IR5 model, regardless of whether you use in sample or out of sample, you end up with the same 11 countries which there is evidence of strong predictability. And of course, I also showed that when you include structural breaks, when you do regimes, the results hold. Right? So what I have shown so far is that while there has been mixed evidence when you use financial ratios, there's no such thing as mixed evidence when you use the type of technology-based factor that I propose here. There is conclusive evidence of predictability, which gives investors more certainty in terms of choosing what they should be tracking in order to forecast stock market returns, right? The second implication, so that was the first implication of what I have told you so far. The second implication comes in the form of a question. And that question is a subset of my research question that I put earlier, is does the statistical evidence favoring strong predictability have any economic meaning? All right? So if you were an investor, you would be now at this stage asking me, well, how you can make use of this model that I have proposed on technology based and invest in one of those 12 countries' stock market, right? So the question then, in other words, can be put more simply is, can investors use the technology based forecasting models I have proposed here to arrive at successful trading strategies? Can you develop successful trading strategies, right? Can you take informed investment decisions based on the model I propose? So that's the question I will try to answer in the next few slides. And I guess the way to think about this before we actually look at the results is to say, I have a portfolio of 12 countries, right? 12 OECD countries. You could invest, so you have two options. You can invest in all of those 12 countries. So if you had $1 million to invest, so I'm trying to give a practical angle how this thing works in practice. If you had $1 million to invest and you trust my model and I have convinced you that this is the way to, you can then decide, and of course you want to diversify your risk, so you invest in all the 12 stock markets. The way to think about that is, what should be your portfolio weight? In other words, what amount of your $1 million would go to each of those 12 markets? So one simple way would be, you could say, I'm going to equally divide it into the 12 markets, right? That would be the way. If you don't know anything about these markets, like what I'm going to show you, the best position to take is to equally invest in these markets because you don't have any other information, right? But once I show you this information, you will know exactly which market is the most profitable, right? So you might want to put 50% of your 1 million in that particular market and accordingly adjust your portfolio based on the information I'm giving you. Okay? So that's what you do when you let others invest on your behalf, like funds or what have you. You let them decide your portfolio weight, right, based on the modeling that they do, forecasting that they do, right? So let's see how this turns out. Okay, so I assume there's a mean variance investor. So there's a utility function is a quadratic mean variance investor, which is a common way to think of investment in this space. I exclude Denmark. Why? Because there is no evidence that technology has anything to do with the Danish stock market. I estimate an investor's portfolio, which is an increasing function of forecasted returns. So if the forecasted returns are positive, so if I forecast the US market and I show you that the forecasted returns are positive, you would want to invest more in the US market, right? Because the returns are positive, means you're going to get higher returns. So it's an increasing function of forecasted returns and a decreasing function of market volatility. So as the US market becomes more volatile, you are going to withdraw your funds, your investment from the US market and look for a more stable market, right? So that's why it's a decreasing function. So the weight, in other words, the amount of dollars you put in the US market would increase if I tell you that the forecasted returns are positive. It will decrease if I tell you that the volatility is increasing, right? And it is also a decreasing function of the risk aversion factor. So what is that? Well, that is the level of risk that you are prepared to take. Okay? If you are not prepared to take a lot of risk, then if the risk aversion factor goes up, right? Think of this as the Standard & Poor's credit ratings. Okay? If the Standard & Poor's credit ratings is downgraded for US market, if you are not a risk taker, you're going to withdraw your funds from the US market, right? So your portfolio, in other words, the dollar amount that you spend in the US market would decline. And vice versa if you want to take risk. Okay? So the portfolio weight is very simple. Only 3 factors dictate your portfolio weight, which is quite common sense. Forecasted returns. If it's positive, you get more dollars in that market. Market volatility. If the volatility is increasing, you're going to reduce the weight. And your behavior, your decision on how much risk you want to take. Okay. And so the question is how we compute market volatility. So forecasting. This model that I propose will give us forecasted returns, right? The market volatility, you can use a number of different ways to compute market volatility. One way is to take a rolling window of returns and compute variance, and that's what I do. Another way would be to take a gauge variance. And there are, of course, other measures, but that doesn't matter in this portfolio weight. They all will converge to some sort of similar weight. Some assumptions I make, right, which is quite common. The first thing is I assume there's no short selling, such that the portfolio weight would always be between 0 and 1. So if you had $100 to spend, you can either spend, $100 to invest, you can invest 0 or maximum of 100. So there's no short selling or borrowing. So you can't borrow and invest. Had I used monthly data, I would be rebalancing if I wanted to every month. Similarly, if I had daily data, if I wanted to, I could rebalance the portfolio every day. But the point here is that every time you rebalance, there's a transaction cost. Every time you change the weight of your portfolio, you switch from one asset to another or to a combination of assets, you have to pay transaction cost, right? The nice thing with yearly data is that the transaction cost is minimized. So you can get a good feeling of what the returns would be if you change portfolio once a year. Okay? I do model transaction cost of 1%. So I'm assuming that transaction cost every year for changing the portfolios would be 1% of the trading volume. Profit, so how do I compute the profit? So then it becomes very simple. I have the portfolio weight. Okay. So if I compute the portfolio weight, remember how the portfolio weight is an increasing function of forecasted returns and a decreasing function of market volatility, your risk aversion factor. If the portfolio weight we know would be between 0 and 1. So if it's 0.5, it is telling you that 50% of your 1 million will be investing in the risky asset, and the balance of the 50% would go to the risk-free asset. So think of PW as the portfolio weight. So if the portfolio is 0.5, then you are investing 0.5 in the stocks, so the US stock market, and the balance in the risk-free rate. Right? When I do that for each of the countries, 11 countries, ignore Denmark, the profits are in this range, 4.11 to 7.50%. So had you given me your 1 million, I would have given you a return in that range. Right? So yeah. Yeah, okay, I'll come to that. So here is the, here are the profits by country, the 12 countries. And these are profits based on the first measure, which was growth rate. And here are the profits I use the IR5 model. Okay, so you can, if you use the results from here or from this model, investing in the UK market would have given you the most profit. So if I had invested your dollars in the UK market, the annualized return is 7.5%. Okay, and the minimum you would have got is about 4 point something, so 4.11 US market would have given you. So this is what I was saying, that if you trust the model that I was proposing compared to a historical average model, and why would you trust it? Because I have already shown you in reaching this that the forecasting error was lower from the technology-based model, right? So of course you would choose the model that gives you the least errors, right? So statistically I had already convinced you that you should not be looking at a historical average, right? And then the question here is that where exactly do you want to invest? Okay, so if you wanted to maximize your returns, you know where you would be choosing, or you can decide to choose the top 5 markets from here. Right? So whatever the investment decision is, what this does is it gives you a set of information that you can use to devise your portfolio. Right? Where exactly you want to invest, whether it's one market, multiple markets, top 5, top 3, you can choose from here. And okay, so then okay, so what I've shown you now is what I've given you now is a statistical story about predictability and how technology-based factors or technological innovations can help you predict the stock returns. And I've also shown you profits, right, that can be made by devising trading strategies using the model that I'm proposing over a competition model, which is always assuming that there's a naive investor who does not have any information. So use the historical average. I want to talk about, before I take questions, I want to talk about the robustness. Okay? So to begin with, there's 2 different measures I have used, right? And what I have shown is that there's strong evidence of return predictability. I used 2 different sets of statistical tests, both in sample and out of sample, and I end up showing similar results in terms of no predictability for Denmark and evidence of predictability for other 11 countries. So in that regard, compared to financial ratio based predictive regression models, this model that I'm proposing works better in a historical framework. Okay? Of course, this type of historical analysis has not been done with financial ratios, so you would never be able to directly compare, simply because there's no historical data on financial ratios going back to 1870s, right? So there is no direct comparison, but what comes out clearly is that here we have a reliable model. I told a story about structural breaks and how in-sample evidence of predictability holds even when we allow for structural breaks, and also when we use the structural break to subsample the data. Right? Now, an additional test I do, so far I've been talking about excess returns, forecasting excess returns. I then also forecast raw returns. And so raw returns are simply returns on the market, not inclusive of the risk-free rate. So forgetting about the risk-free rate, right? And also real returns. So this is saying adjusting for inflation. Okay? And these things make sense because I'm taking sort of 100 odd years of data where the macroeconomic environment has changed quite drastically in some of these countries. And part of the macroeconomic story is inflation. And taking real returns could simply change the story that I'm trying to tell about predictability. So I run all those models that I showed you by changing the dependent variable from excess returns to raw returns and real returns. And what I find is that the story remains the same, except for one or two countries here and there when I do subsampling. But the broader story at the end of the day remains the same, that predictability holds, and Denmark is quite isolated from this group of 12. Then another robustness test I do, you'd recall that I had used 50% of the sample for forecasting, 50% of the in-sample for forecasting. I changed that to a shorter sample of 30%. Right? And I wanted to see if I reduce the in-sample and forecast for a longer sample period, rather than 50-50, I had 30-70. Right? So I had 70% of the sample to forecast. So out of 100 years of data, I used the first 30 years of data for in-sample, and then I forecasted remaining 70% or 70 years. Right? Then what I did the other way around. I took 70% as in-sample, so 70 years of data as in-sample, and then I forecasted for a smaller sample period of 30 years. And again, what I found, so I repeated all the tests and details in the paper, that the results don't change. And again, Denmark stands out completely. Right? Then perhaps this is an issue that relates to a question that you asked about different levels of investor risk aversion. In the mean variance utility function, the only way to capture risk is through the investor risk aversion, which comes in the denominator of the portfolio weight. So the portfolio weight, the investor's risk, is in terms of how much you are willing to commit to a market, right? In the absence of short selling or borrowing. So that's the only way, because your weight, how much you decide now to invest in a particular market, would be dependent on how much risk you are willing to take. Right? If you are going to take zero risk, for example, then you will not invest in the stock market at all. You will invest 100% of whatever funds you have in the risk-free rate, right? And then get a 1.2% guaranteed return. Okay? So the level of risk, so this is again part of the robustness story that I deal with, different levels of risk aversion. So what I do in the portfolio weight, so you can think of this as the numerator will have the forecasted returns. The denominator will have market volatility multiplied by the risk aversion factor. Right? As you increase that risk aversion factor, you will be investing less and less in the stock market. Okay? So I consider the only way I can consider different levels of risk is to increase the risk aversion factor. And typically what in the mean variance utility function, the way that is captured is you start with a low risk from 3 And theoretically, people have shown that 3 represents a value of 3 in the stock market when returns are in percentage form. Represents a low risk investor, a medium risk is 6, and a factor of 9 represents a very high risk investor. Right? So I do all those robustness tests to capture how the investor sentiment about taking risk in the market is going to influence that. And yes, there's changes in the profits. As you take more risk, profits increase. Right? So I find what is consistent with theory in there. But the fact remains that the market is profitable provided on how much risk you are willing to take, right? Which is what you would expect in this. So there's no surprising result in that, because you would expect that profits decline as you take less and less risk in the market. Right? Okay, so that I think concludes it. Yes, that's where I'll stop.
Okay, so if you have any questions, you may approach the microphones over there.
Good morning. I'm Kwalitai Bunyasena from Rajamankara University of Technology, Pranakon. I'm an energy economist and I love econometrics. So, do you mind, today I have 2 questions. Do you mind showing me your model again, please? For a TEC model. Yes, so I think your answer might increase my knowledge for econometrics. You have 2 controllable variables, right? GDP and TS. Okay, why do you use these 2 variables at time period T-1 rather than T?
Yeah.
First question.
Okay, is that only question? You said you had 2 questions.
Okay, 2 questions. Because you employ really long time period that are about 100 years. So do you have problem about non-stationary? How to deal with take different or lock or something?
Thank you. 2 very good questions. So the first question is asking me why I use the leg -1, right? The reason is I want to know this is the future. This is the 1 year ahead, right? So think of this as 2017, right? I want to know how the technology variable in 2017 would behave conditional on what the GDP was in 2016, in the past, right? Because the past information will help me accurately model the expectations or the behavior of technology, right? So I leg it T-1 and also T-1 here, so going back 1 year. So it's effectively saying that you go back 1 year, so whatever has happened in the past should influence the technological innovations going forward, right? If I had not taken the leg, then I would not capture the effects of these macro variables, macro and financial variables, on the technological expectations. Okay, I guess a related question could be why have I stopped at -1? Why have I looked only 1 year back? I did some test on that. I looked at 2 years, 3 years, 4 years. But the best adjusted R squared of the model was when I used 1 year. So a lot of TEC was explained when I used the 1 year. Okay. So that's the response to the first question. The second question was about the stationarity. So it's actually quite simple. So you start from here, which is easy to see. It's the growth rate of real GDP. So it's I0. It's stationary, right? Growth rate of anything is stationary, except perhaps for consumption, right? There's some controversy about consumption expenditures. But anything else you take in growth form would be stationary. So that's I0. This is the term spread, so that's I0. This is the market returns. Again, it's returns minus the risk-free rate, that is I0. And the technology factor, this is a return-based technology factor. It's return-based, so it's I0. Right? So everything is I0, it has to be. Okay. Yes.
Okay, some other questions?
Yeah.
And your RTF. What I saw quickly was a lot of volatility in RTF, what you showed. And I thought that some kind of ARDL or NARDL must be introduced here to satisfy Pesserum kind of stuff here. And did you do that? That's the question.
No, I didn't. What I did is to control for the volatility, I did two things. Where is that? Let's say. Yeah. So what the question is saying that the RTF measure I have looks volatile, right, from the plots, and I use that as a predictor. Australia, US is even more volatile. So the question is, how do I handle this, right, in the model? Well, the nice thing that I don't have to worry about the volatility too much is because this is annual data. So if you did a heteroscedasticity test on this annual data, you find there's no heteroscedasticity. So what looks graphically as a very volatile series is actually statistically not a volatile series because it's annual data. Okay. So I did so to answer your question directly, I did a test for volatility. There's no heteroscedasticity. But having said that, when I ran the regression model, this one here, I controlled for standard errors using the Newey-West procedure, which allows not only to control for heteroscedasticity, but any autocorrelation that may be due to the lag dependent variable. Right? So I did control that because, yes, heteroscedasticity is not there, but autocorrelation is quite possible. Although I did not test autocorrelation, but I adjusted the standard errors in the estimate. So the predictability results I showed you, they actually take into account heteroscedasticity and autocorrelation if there are any. Although the statistical tests say that there is no heteroscedasticity, which is just as expected because of annual data.
Okay, other questions, please?
I'm sorry? Sorry? Yeah. No, it has. So when I did the regime analysis, you see with the structural breaks picks that computational science.
To compare the regression model.
Uh,
Because in my view, I think the regression model is just for the linear relationship.
yes.
But if you use like the neural network or other model, it can like fit for the relationship that not linear.
Yeah. Okay. I see what you mean. So you think that this model is a linear model? This model here you are saying is a linear model.
I think that is something that like neural network or other thing that you can like just use to compare, and it might find something that can fit. And this one is like 100 years, so
Yeah.
a lot of data. And if you use that kind of model,
Yeah.
you might see something, because in my view, I do the prediction as well, but I use the different model. But I still looking for what it fit to make the return in stock market. So just different view for you that if you use that one, it might fit, or this model is better, but just the evidence that you can see the difference between the 2 or 3 models.
Yeah, okay, I see your point. There's two things with what you are saying, right? One is you only use different models if you can't find support for your hypothesis. If you can use a simple model to find evidence for your hypothesis, there's no need to use other models, because what is the motivation? There's no motivation, right? We already find that there's predictability except for Denmark. And if you can explain, like we do, why Denmark is not predictable, because Denmark hasn't invested in technologies at the same rate as other OECD countries. So if you can use a linear simple model, like this is linear, this is a non-linear model, right? This is a linear model. This is non-linear because I include the structural break. So I'm not doing a non-linear model in terms of non-linear least squares, but I am capturing any non-linearity through the structural break, which is what matters for investor purposes, right? So I guess I can see, I don't disagree that you can use whatever models. If you start using alternative models, you can have 100 models here, right? And the need for, the way I would see this is that the need for alternative models comes about when you are not able to find support for your hypothesis. Okay? And then of course that is also a motivation to develop new models. Okay? So I guess what I'm quite satisfied with the results I'm getting, because I'm able to get answers to the hypothesis. Had I not, then that would open up questions about maybe I am missing some things here, like what you are saying. Maybe I'm not using the right model. Okay, so I guess there has to be a motivation to move into the literature that you are talking about, which I am not familiar with to begin with. The second thing about that is you need to have a practical relevance about your model, such that it's a model that can be used by in practice, right? And if you can achieve the objective of your research by using a simple model, then of course others can use that very straightforwardly. Again, I'm not aware of that literature that you are alluding to, but my point here, and that reflects the second part of my analysis, where I do the trading strategies and forecasting. This becomes a very straightforward model to forecast, because ultimately you want somebody to use this model, right? Otherwise it makes no sense from a practical point of view. So I guess there is, to summarize, I guess there's scope to expand, but perhaps not in this literature, because I show that everything works here in a nice way, right? So I don't see any reason why I would look for alternative models when I can test my hypothesis with the success that I'm able to achieve here. Now you want to recall the fact that it's not the model that is making the difference here. It's not the model. As I said to you, if I take this away, the return-based technology factor that I have computed, and I simply use patent growth rate, there's no predictability. Why? So you could say, why don't you use nonlinear model, right? But that's not about the choice of statistical model. It's about the choice of the predictor. So you see what I did? I computed this return-based technology factor in an innovative way. So I borrowed some sort of literature from econometrics to estimate that there. So instead of using the technological growth rate, I just estimated that over time and made it a technology-based factor, right? So that it is also I0 in that setup. And that works perfectly. So to this model, No? If I remove this and if I had no knowledge about how to compute this return-based technology factor, I would be concluding here that patents do not predict stock returns, right? And then somebody would be saying, okay, why don't I use nonlinear models or some sort of wavelength forecasting models and what have you, right? That would be a place for that kind of discussions. But what I have shown is that it's not the method, but it's actually the information variable. If you don't have a variable that captures the information about technology, there will be no predictability, right? You can only predict something if you have information about that. So my focus here is more not on the econometrics or the statistics of it, but more what represents the market's expectation about future technological innovations. Right? How can you capture information? Is it patents granted or some other version of that? I show that you can't use patents granted because patent granted today will have an effect on the market in 10 years' time. Or who knows, right? It may be 15 years' time depending on the nature of the patent, right? So what it means is not a different statistical method to deal with it. What it means is to look at where is the information coming from and how best you can capture that information about the technology. So that's why I propose this idea of computing it in this way. And then I show that, yes, this is very rich in information. Right? This is very rich in information, which is this. Here. See, this reflects the market's expectation of the technology. Right? So sometimes it's not only about the statistical methods, but also about the information content that is inherent in whatever you are looking for, which in my case is the technology. Okay.
Thank
Okay.
you for sharing your view. Thank you.
Okay, thank you so much for those questions. And also, I would like to say thank you to Professor Narayan for sharing us his knowledge on technological innovations and stock market returns.
ค่ะในโอกาสนี้นะคะขอเรียนเชิญท่านอธิการบดีมหาวิทยาลัยเทคโนโลยีราชมงคลพระนครนะคะรองศาสตราจารย์สุภัทราโกษยการนนท์ค่ะมอบของที่ระลึกให้แก่ท่าน Keynote Speaker นะคะ Professor Parash Narayan ค่ะ
Okay, so ladies and gentlemen, before we go for lunch break, let me just inform you to please bring with you your coupons. So we have there yellow, blue, and white coupons. So for the yellow coupons, please proceed to Ratanakosine room at the first floor. For the white coupons, please proceed to the mezzanine of this hotel. That's also at the first floor. And for the blue coupons, please proceed to the first floor and look for the elevator bringing you to the other side of the second floor of this hotel.
ค่ะสำหรับการประชุมวิชาการนานาชาติของเราในช่วงเช้านี้นะคะการบรรยายพิเศษก็เสร็จสิ้นลงในช่วงนี้นะคะสำหรับในช่วงบ่ายค่ะยังคงมีในส่วนของโปสเตอร์ Presentation และ Oral Presentation นะคะสำหรับการรับประทานอาหารเที่ยงของเรานะคะผู้เข้าร่วมการประชุมทุกท่านนะคะจะได้รับคูปองในตอนที่เราได้มีการลงทะเบียนก่อนเข้างานกันมาแล้วนะคะคูปองอาหารเที่ยงจะมี3สีด้วยกันค่ะสีเหลืองนะคะจะเป็น VIP นะคะจะรับประทานอาหารที่ห้องรัตนโกสินทร์ค่ะอยู่ที่ชั้น1สำหรับสีขาวนะคะก็จะอยู่ที่ชั้น1เช่นเดียวกันค่ะแต่ต้องเดินออกไปตรงที่ชั้นลอยนะคะและถ้าท่านใดได้รับคูปองสีฟ้าค่ะสำหรับสีฟ้านะคะก็รบกวนทุกท่านเดินลงไปที่ชั้น1เช่นเดียวกันค่ะแต่เปลี่ยนลิฟต์นะคะ